so let's look at another bit of data regarding pegylation. And we'll look at figure 5 here. Alright, so first, let's look at the figure legend. This is an immunodiffusion plate. Alright, I'll have to tell you what an immunodiffusion plate is. But first, let's identify all these little holes. So basically, this is a plate. It's more like an agar dish. So you have a semi-solid medium with holes cut out. And then the scientists put different things in each one of the holes, and they saw how the things they put in the holes diffused throughout this agar. So, looking at the figure legend here, we've got catalase. So unmodified catalase in A. We've got pegylated catalase in B. We've got anti-catalase serum in C. So these are antibodies that are specific for catalase. Excuse me, these are antibodies derived against non-pegylated catalase. And then in D, we have antibodies raised against pegylated catalase. So anti-peg catalase. All right, so they put these different substances in each one of these different wells, and then they see how the substance diffuses throughout the gel. Now, for what you'll also see here are these lines, okay? These semi-opaque lines compared to the rest of the gel. Those lines represent immune complexes. So anytime one of these antibodies finds one of these other things that they're specific for, they'll form a big complex, and that complex is big enough to diffract light. And because it's big enough to diffract light, we can see where the reaction is actually occurring. And so these lines represent antibody-antigen recognition. Okay, so given that introduction, let me ask you this question. What does figure 5 say about pegylated proteins versus non-pegylated proteins? Okay, got some disagreement here. Those of you that said, go back. Those of you that said A, why did you say A? Pegylated proteins are more immunogenic. Why?
I'll say that because you say the lines represent antibody-antigen recognition.
Okay, so we've got, okay, the lines represent antibody-antigen recognition. And so what is it about where the lines are that make you think that pegylated proteins are the most immunogenic, are more immunogenic than the native protein? All right, so again, we have regular old catalase in A. We've got peg catalase in B. We've got anti-catalase in C, and we've got anti-peg cat in D. All right, so are these things going to diffuse unidirectionally? What do you think? Well, we covered diffusion, right? Had like 4 hours of diffusion. Do things dissolve in a direction? Is that a vector component? Or is diffusion directionless? It's directionless, right? So anytime you put a substance in a circular well, it will diffuse in concentric circles. The concentration is the highest at the well, and as you get farther and farther away from the well, concentration is less and less. Okay, how about B? Give me somebody that will defend B for me. Pegylated proteins are less immunogenic.
The way the lines are on there, it looks like it's A meeting the antibodies, whereas there's not a line between the B's meeting the antibodies.
And I would agree with that interpretation, right? So if you've got A diffusing, let me draw on this slide. All right, you've got A diffusing in a concentric circle, and you've got B diffusing in concentric circles. You've also got C diffusing in concentric circles. So all of these should have an equal opportunity to meet, but the only point in this data where we see antigen antibody recognition is implied by where the diffusion front of A meets the diffusion front of C, right? If the substance in B was just as immunogenic as the substance in A, what would you expect to see? Expect to see a big old line right here too. Probably one right here as well. And we don't see that. So I say, yeah, for sure, B is correct. Pegylated proteins are less immunogenic. They do not seem to be detected by either the anti-catalase or the anti-pegylated catalase antibodies. What about C? A lot of you liked C. It's possible there's more than one right answer. Greater area around B. You mean this white, kind of white ring that you see? Okay, why do you think that means that there's more diffusivity? Okay, well if they move further, so that's a good observation, right? So what Shannon is pointing out is if you compare A to B, B kind of has this white halo, whereas A does not. Maybe a little bit on the edge, not a whole lot. So we see this opaque region that's right around B, and what does the opaque region mean?
Antibody antigen recognition.
Antibody antigen recognition. So it appears that the antibodies have traveled from C and B, but it appears like maybe whatever's in B didn't get very far. Right? Otherwise, we follow the assumption of the answer that B has, that pegylated catalase has greater diffusivity, right? We would expect to see a line that's closer to C and D, right? Means that the diffusive front is moving more quickly for B than it is for A. In contradiction to that, what we see is actually that whatever's in B doesn't seem to be getting very far, that the antibodies have to move to it. So I would argue that if anything, D is more correct. Pegylated proteins have less diffusivity. It seems like they're having a harder time getting out of this well and diffusing through this agar substance. Okay, so to recap, it appears that from this data we can say that pegylated proteins are less immunogenic, and there does seem to be some evidence that pegylated proteins are less diffuse or have less diffusivity. Okay, next figure. We've got figure 6. So we're looking at this one. We've got some in vivo data here. All right, so what the experiment is here, let's look at the figure legend. We again are looking at the blood circulation life of catalase, non-pegylated catalase, represented by the X's. Let's just call this peg, or excuse me, catalase. And pegylated catalase. In mice. Okay? So the experiment goes on day 1. The animals are injected with the enzyme, either the catalase or the pegylated catalase. Right? So we have 2 cohorts of animals. One cohort is injected with the pegylated catalase, the other is injected with the regular catalase. And then they start taking time points. All right? So if you look at the x-axis, all the way here on the bottom, looks like they start taking blood as early as 15 minutes after injection, and then they'll take a 12-hour time, maybe a 6-hour time point, 12-hour time point, 24, 36, 72, on and on and on. And then we have A, B, C, and D. We repeat this assay on day 30. We repeat it on day 60. And we repeat it on day 90. And so what they're doing is on each one of these days, they repeat the experiment. They give the catalase mice regular catalase, they give the pegylated catalase more pegylated catalase, and they're taking samples from the blood, and they're assaying for catalase activity. Okay, so for this data, what does this data say? About pegylation. Actually, this is probably figure 6. Figure 5. Okay. Most of you said A, pegylation increases serum half-life. Why A? Why does it? What about the data tells us that it increases the serum half-life?
The pegylated version
version is still there on day 90?
Still there on day 90, but remember on day 90 it gets these mice get a re-injection, right? So on each day, right, we're asking day 0, day 30, day 60, day 90. Each one of those days it's being injected. It's all right. I mean, you're right, it is there. We have catalase activity.
After so many hours, it's still in the blood.
So many hours it's still in the blood. So even if we look at day 0, or any of the days really after it has injection, they assay out to 72 hours, and even out in 72 hours we have detectable catalase activity for the pegylated version, right? If we compare that to the non-pegylated version at day 0, we lose the amount of detectable catalase in the blood after about 12 hours. Let's see. I'd like to point out here that we lose detectable amounts of catalase on day 0 at 12 hours. We lose detectable catalase on day 30 at about 6 hours, maybe even 3 hours. And it looks like on day 60 it's even shorter. So for non-pegylated catalase, on each subsequent injection, the serum half-life seems to be decreasing. Why do you think that is? Is this human catalase or mouse catalase? It's human catalase. So we're developing this drug for human therapy. So we want to give humans human enzymes. So we're injecting a human enzyme into a mouse. Yes, ma'am.
Is it because the mice are building up resistance against the human catalase?
Absolutely, very good. All right. So just like we talked about in immunology, as soon as you inject something foreign into your body's going to start making an immune response against it. In this case, the immunocompetent mouse is developing antibodies against catalase. So the first time it sees it, it's going to take a while for the mouse to clear it out of its system. But each subsequent exposure, the mouse gets a little bit better at getting rid of this foreign antigen. Right? The antibodies go through somatic hypermutation. They go through affinity maturation. They go through isotype switching. So the mouse antibodies work just like our antibodies. Every time they go through this, their immune response to this antigen gets better and better, so that by day 90, the fourth time that this mouse has been exposed to catalase, it takes care of that catalase almost instantaneously. And even as early as 15 minutes, there's no detectable catalase activity because it's all been consumed or neutralized by the mouse antibodies. Can we say anything from this data about immunological memory as it pertains to pegylated catalase? All right, some of you wanted to say C or D. Is there anything to be said about immunological memory from this data?
For the not pegylated, I mean, like you said, you can tell that it's building up immunity. So.
Yeah, so there's probably something to be said for the non-pegylated version. I don't think we can say anything about the pegylated version and its ability to stimulate or decrease immunological memory. Right? We saw in the previous data, this immunoassay plate, that the pegylated version of the enzyme is really bad at being detected by antibodies. Right? So this data does not directly inform any of our assumptions or hypotheses about immunological memory. Yes?
So if it did, what would you expect the graph to look like over time?
Great question. What do you think? So first of all, let's be exact in what we're talking about. If it did what?
If the pegylated version did increase immunological memory.
Okay. If the pegylated version did increase immunological memory, how would you expect the data to look differently?
Wouldn't it look like what our catalase looks like?
Very good. It would look very much like, well, it would have a similar trend as our non-pegylated version, right? You'd see a certain serum half-life curve at day 0. If that was able to simulate immunological memory, that curve would be more shallow on the second administration, even more shallow on the third, and probably non-existent on the fourth time it was administered. Good question. If that had been the data, I would agree with you, yes. For those of you that answered D, yes, maybe this data does show us something about, or does imply something about pegylated catalase's ability to stimulate immunological memory. But because even on day 90, the fourth time that these mice have seen pegylated catalase, we still have a serum half-life that is comparable to day 0. The chances that this stimulates immunological memory at all is very unlikely. So, I would say from this data, we can argue that pegylation increases serum half-life. Yep.
The fluctuation in blood catalase activity for the pegylated proteins, like for day 0, it actually gets a little bit lower than day 30.
Sure.
And then it goes back down. Is that just due to the average, like the immune health of the mouse on that day, like whether or not the immune system can respond?
Sure. It's a legitimate question, right? Why do we see so much variability from day to day? The easy answer is this is what real data looks like. Right? There's just a huge amount of variability when we're talking about doing experiments in animals. And these are genetically identical mice, right? That probably are all performed at the same time of day. But even then, there are going to be small changes to diet, maybe small changes to environmental conditions. If they're using female mice, you have to take into account hormonal cycles. So there's a lot going on in a living organism that makes the data very noisy, right? So that's where statistics come in. They didn't perform any statistical analysis on this data, in this figure at least. But if we could take averages from all these mice. We could calculate the half-life from each day, and then we could say, based on the variance of our half-life calculation, are any of these half-lives statistically different? All right, so let's review what we just learned about pegylation from all of these experiments. So, we saw in the first figure, pegylation reduces proteolysis, makes it more resistant to protease degradation. It appears to reduce immunogenicity. It increases the half-life. And an item about pegylation that was not shown in any of the data, it also increases solubility. Right? Because of the polar molecules on that pegylation moiety, it is going to be more likely to interact with an aqueous environment, so pegylated proteins have greater solubility than non-pegylated proteins.
Dr. Walls,
Yeah.
can you not move forward because we don't have the slide?
Sure. Tell me when. Yes.
So with the increase in solubility, is that because the PEG has, or the PEG has, the ability to do hydrogen bonding?
Yes, right? So if you go back a couple of slides and you look at the chemical description of polyethylene glycol, there are H-bond acceptors and donors. All right, so the reason we spend half an hour on pegylation is because this is a very common modification of a lot of the biotech products that you'll work with, right? So filgrastim, colony stimulating factor that's used in a lot of cancer patients after they've undergone systemic ablation of their HSCs. That comes in a pegylated form. We've also got pegylated interferons used to treat various viral disorders. L-asparaginase used to treat leukemia, uricase used to treat gout. All of these come in pegylated versions, right? The big advantage, at least therapeutically, is this guy right here. It increases the half-life. So all of these proteins have to be administered via injection. Sometimes they even have to be administered under very close control, like an infusion device, something that can't be done at home. And so if you have a pegylated version of a protein that's going to stick around in the serum much longer than a non-pegylated version, that's less pokes, it's less injections, it's less oversight of the patient. So in terms of patient compliance, pegylated versions of these proteins are much more desirable. Okay, so let's move on to other types of biotech formulation. The next subject I want to talk about is biodegradable microspheres. So we have a couple of FDA-approved versions of these. Both of the FDA-approved versions use a compound called polylactic acid, polyglycolic acid, which no one ever says. This is always PLGA. All right, these are three-dimensional microspheres. So they are on the micron order of the scale, and the drug is sort of embedded within these microspheres. The idea is that after a single injection, the microsphere sort of stays implanted within the muscle, and that over time, this PLGA wears away, and as the PLGA wears away, drug is released at a constant rate. All right, so again, just like the pegylation, this is a way of maintaining a certain dose for a long amount of time with just a single injection. The two FDA-approved examples we have of this are leuprolide, which is luteinizing hormone-releasing hormone agonist for prostate cancer. These patients only get one of these microsphere injections every couple of months. And then GLP-1, glucagon-like peptide 1, also known as Bydureon, is a microsphere formulation used in the treatment of diabetes. All right, on a slightly different scale than these molecular formulations, we have mechanical mechanisms of delivery. All right, and in particular, we have the mechanical pump. It's used by a good number of diabetic patients. Again, all of these formulations have to be injected. The vast majority of them cannot be ingested. They're not available by oral delivery. So we have to have some mechanism of introducing these drugs by parenteral formulation. Okay, the mechanical pump allows a lot of user control. Right? You have one site of injection, but you can get a lot of doses out of that one site. This is a device that patients typically wear on their person. It's about the size of a pager. You guys have no idea what a pager is. But it's preferable, right? It's something that just clips to your belt, sticks in your pocket, greatly reduces the number of injections, still requires a significant amount of patient input, right? The patient is still clicking buttons on the pump postprandially every time they eat, if this is insulin that we're talking about. One step up from that are these biosensor pump combinations. All right, so these I think are super cool. I'm not diabetic, but if I was, I would like to think I would use them because they just seem awesome. So this is a combination of the pump that we saw on the previous page and a glucose sensor. All right, so you have one stick for your pump, you have another stick for your sensor, and the two devices sort of communicate wirelessly. It's kind of like having an artificial pancreas, as the marketing says. The advantage of this is that patients no longer have to stick themselves, however many times a day to monitor their glucose. They just have one stick that is constantly monitoring their glucose, and that will talk to the mechanical pump. So when the glucose gets low, after glucose gets high, we pump in a little bit of insulin. If glucose gets too low, we back off. The ideal formulation, however, for insulin is a self-regulating system. So this is an idea that's been around for decades. It has a lot of attractive attributes. This is a picture that I pulled from a paper that was, I think it was published about 15 years ago, so to give you a sense of how long this idea has been around. The idea is to have self-regulated insulin, right? So instead of having user control over when and how much insulin is injected, you simply have insulin, a formulation of insulin that will respond to the environment. It will respond in your body to how much glucose is present or absent. So the idea that's been thrown around for a number of years is shown in this figure, okay? So we have a Cephalose bead. This is basically just an inert molecule that you can attach things to. And that is conjugated to a protein called concanavalin A. And con A will bind to sugars. It's a lectin. I'm talking about lectins in immunology. Lectins are just proteins that bind to different sugars. It will bind in its initial formulation to glycosylated insulin, so insulin that we have conjugated to a sugar. And the sugared part of that insulin binds to concanavalin A, but it has greater affinity for regular old glucose. So when this substance sees some glucose, a high affinity glucose binding will displace the glycosylated insulin. And the insulin is free to go about and do insulin-like things and lower blood sugar. There's no user input, right? You just have one injection of this formulation, and it will respond to circulating levels of glucose in the patient. This is known as competitive desorption. It's a cool little idea that we just haven't gotten to work yet. All right, so all of these types of formulation, whether it be the chemical modification with PEG or some other substance, the microspheres, the pumps, the self-regulating systems, these all control rate. Right? These all control the time with which the drug is delivered inside the body. These next couple of slides are going to focus on targeted delivery. All right, so one of the nice attributes of the molecular age is that we are able to devise or design these in vitro antibodies that have great specificity, much greater specificity than almost all of our small molecules. Right? This is by design. This is what adaptive immunity does. It creates an antibody that is very, very specific. And because of that, we can use that attribute of antibodies and their high degree of specificity to retarget otherwise potentially toxic molecules. All right, this has been done in the oncology field most efficaciously. We have 4 different examples of targeted oncological drugs that otherwise would cause systemic side effects. All right, so all the horror stories you hear about conventional chemotherapy, makes your hair fall out, disrupts your GI tract, causes plaques on your skins. All of that gets taken away when you simply conjugate that toxic molecule to an antibody. All right, so the example here at the top, we've got Gentuzumab, ozogomycin. So ozogomycin is an incredibly toxic drug. It'll cause all those terrible things because it's nonspecific. It's got a nonspecific mechanism of action. It'll just kill cells. So rather than just killing everything and hoping that we get rid of the cancer first before we kill the rest of the cells, we conjugate it to a monoclonal antibody. And in this particular application, it's targeted against CD33, which is a marker of B cells. Acute myeloid leukemia is a B cell cancer. So this drug compound, was targeted specifically against B cells and affected the B cells exclusively because of its targeting capability. Same sort of paradigm in brentuximab vedotin. This is an anti-CD30 antibody for Hodgkin's lymphoma, conjugated to a very toxic molecule called vedotin. Trastuzumab emtansine, anti-HER2 antibody, so Herceptin, treatment for breast cancer, conjugated to emtansine, another very toxic molecule. The most fun one on this list, though, is the one at the bottom, denileukin diftitox, which is an IL-2 or interleukin-2 diphtheria toxin. So this is used as a treatment for cutaneous T-cell lymphoma. We know from immunology that T cells are very dependent on IL-2 innervation, so they have a lot of IL-2 receptors. So the idea here is you molecularly conjugate IL-2, which is going to be the targeting ligand. It's only going to go to IL-2 receptor. You conjugate it to the toxin that's produced by diphtheria. So this conjugated toxin binds to IL-2 receptor. That gets endocytosed by the cancerous T cell, and the toxin kills the T cell, but only the T cell, only things that are going to be expressing IL-2 receptor. All right, so that's one example of how biotech formulations can be used to alter targeting efficiency. The other big innovation of the last 10, 15 years has been nanoparticle design. All right, these take a lot of different forms. Here I've given you some carbon-based nanotubes and nanospheres, but there are other molecules, other chemical compounds that make up these nanostructures. The idea behind these is that they are going to be small, right? They're going to be on the nanometer scale, certainly small enough to cross healthy endothelial tissues. We don't want them to be too small, or we want them to be at least smaller than 5 microns, otherwise the macrophages recognize them and pick them up. But the big advantage is that there are a lot of available moieties for us to conjugate things to on these structures. So they kind of serve as like a scaffold, right? And you can conjugate them to drugs, you can conjugate them to targeting moieties, and you can stick all of these on one structure. And as such, they can have a lot of different functionality, right? So if you're targeting cancer, let's say you could conjugate 3 different drugs to this nanoparticle scaffold. You could conjugate something that's going to interfere with DNA replication. You could conjugate something that will interfere with microtubule assembly. Maybe something that conjugates, that interferes with membrane function. And in addition, you can conjugate targeting moieties, whether they be monoclonal antibodies or interleukins that target specific immune cancerous cells. So these represent a lot of promise. We don't have any carbon-based nanoparticle structures FDA approved yet, but they are on their way. Liposomes are here though. Liposomes represent a type of nanoparticle structure. There's a little bit of resistance to calling these nanoparticles because they can range anywhere from 30 nanometers to about 10 microns. They can get quite big and thus not, nanotechnology. Essentially, these liposomes are vesicular structures, kind of like an empty cell. They still have a phospholipid bilayer membrane, but there's nothing on the inside. The attractive features of a liposome are that you can stick drug on the inside, aqueous drugs you can stick on the inside. You can stick drugs within this membrane if they're non-aqueous, right? If they are highly lipophilic, you can stick them inside the membrane. This is done for amphotericin B, which is an antifungal compound. Amphotericin B is very poorly soluble in water. So the only way really to get this drug inside of a human is to stick it in these liposomal membranes and then inject the liposomes. The other attractive feature is that these liposomes can be conjugated on the outside for targeting reasons. We had a quiz earlier this semester talking about doxorubicin, right? A lot of groups have tried targeting liposomal doxorubicin to certain cancer cells to even further reduce the number of side effects caused by that formulation. In fact, Doxil, which is the commercially approved, the FDA-approved version of liposomal doxorubicin, is conjugated to our friend polyethylene glycol. It is a pegylated liposome. All right, so what we'll see, bringing it back to the art, just like in the Pompidou Center, you get a mishmash of all these different techniques. Right? Here we have a liposome that's been conjugated to a PEG moiety, and they all work in concert to kind of combine these different functionalities. The nice thing about liposomes is, due to their size, they basically cannot extravasate into healthy endothelium, right? So anywhere you have a healthy organ, say the heart, healthy organs have very narrow fenestrae in between their endothelial cells. But something like cancer, that's forming new blood cells, new blood vessels all the time, it's going to have very large fenestrations, and these liposomes will be able to extravasate into those tissues. So this is known as the enhanced permeability and retention effect. And it's part of the reason why liposomal doxorubicin works. We have a rather poor idea about what happens to these liposomes once they meet their target cell. And a lot of it depends on what's been conjugated to their surface. So there are a number of different ways that liposomes can actually have an effect on cells. And depending on the lipid components of a liposome, right, so what exact lipids you make that vesicular membrane out of, they can have different mechanisms of entry. In some ways, this is a good thing, right? We can really tailor these liposomes for a specific therapeutic target. In another respect, it's hard to say that these drugs are good because we have a very poor understanding of how they interact with target cells. So for some liposomes, right, they can release their contents outside of the cell and then rely on passive diffusion to get the drug across into the target cell. For other types, we rely on transfer of lipophilic compounds, so actually a fusion of the liposomal membrane with the plasma membrane. We have things like membrane fusion, where after the liposomal membrane and the plasma membrane fuse, that releases the drugs into the cell. And then finally we have liposome internalization, which we think happens the majority of the time with our FDA-approved liposomal formulations, where the liposome is endocytosed or phagocytosed, and then somehow the drug gets across the endosomal membrane into the cell to have an effect. All right, the last slide in this lecture, I'm not sure it has anything to do with biotech formulation, but I couldn't pass it up. I didn't know where else to stick it. I want to talk about Proteus. So Proteus is a company, it's not a drug, and their whole shtick is that they will combine drug formulations with technology, right? What they have done, their first test of this technology has been a combination with aripiprazole, which is an antipsychotic, right? One of the things we worry about when treating people with mental health disorders is adherence. So they go off their meds, bad things happen. So this is a way for healthcare workers, physicians, pharmacists, nurses, concerned family members, a way to ensure that the patient has adhered to their medication regimen. All right. What you see, this is a real picture, not a cartoon. You have the tablet here, which is aripiprazole. There's nothing special about this tablet. It's immediate release formulation. And embedded within this tablet is a little chip, and that chip is responsive to acidic environments. So as soon as the patient ingests the formulation, the drug dissolves and the chip gets activated that sends a signal to this wearable sensor. So it's just like a sticker, a little Band-Aid that the patient puts on somewhere. And it triggers that sensor, so then you can go on your smartphone and you can say, hey, did my friend take their medication today? And if the sensor has received the signal from the chip, the answer is yes. So where this stands right now, Proteus filed an FDA application in 2015. The FDA came back and said, yeah, no, thanks. Thanks, but no thanks. They requested some additional information, which is like a polite way of the FDA saying no. That has not deterred Proteus. They are still going ahead with this technology because of its tremendous potential, right? How many times have you heard about the problem of adherence in any of your other classes? A few times, right? Seems to be a big thing with pharmacists. They talk about it a lot. So if, and I believe it will, when this becomes approved, this could kind of shake up the market. And I think you'll see a lot of formulations in the future incorporating this kind of technology. All right, let's take a 10-minute break and reconvene at 11:05. We've got a short lecture on immunogenicity, and then we'll get out early.